What if you could hover at the edge of oblivion, suspended at the exact boundary where physics as we know it breaks down completely? Imagine floating at the event horizon of a black hole, the point of no return, where light itself surrenders to gravity's ultimate power. What would you really see? What would you experience? The truth is far stranger than Hollywood has led you to believe, and today we're going to take you on a journey to the most extreme environment in the universe. No object in the cosmos has captured our imagination quite like black holes, cosmic monsters that devour everything in their path, even light itself. But the most fascinating part isn't the black hole's center, it's the mysterious boundary known as the event horizon. This invisible line marks the point where escape becomes impossible, where the rules of reality seem to bend and break. Today, we're going to cross that line together. Let's start with a fundamental misconception. The event horizon isn't a physical surface you can touch or stand on. It's a mathematical boundary, a spherical point of no return surrounding the black hole. Cross this invisible line, and you're trapped forever by gravity so intense that not even light, traveling at 185 miles per second, can escape. To understand why, we need to grasp the concept of escape velocity. On Earth, escape velocity is about 25 miles per hour, the speed needed to break free from our planet's gravitational pull. The Moon's escape velocity is much lower, just 5,300 miles per hour, which is why Apollo astronauts could leave its surface with relatively small rockets. At the event horizon, escape velocity equals the speed of light. Since nothing can travel faster than light, according to Einstein's special relativity, nothing can escape once it crosses this boundary. The radius of this point of no return is called the Schwarzschild radius, named after Karl Schwarzschild, who first calculated it in 1916, just after Einstein published his theory of general relativity. For a black hole with the mass of our Sun, the event horizon would be just 3 kilometers in radius, smaller than a major city. But supermassive black holes at galaxy centers can have event horizons billions of kilometers across. The one at the center of our Milky Way, Sagittarius A, has an event horizon about 12 million kilometers in diameter, roughly 17 times the size of our Sun. If you were to approach a black hole in a spacecraft, the visual experience would be nothing like what most movies depict. Forget about swirling vortices or cosmic whirlpools. The reality is both more subtle and more spectacular. As you get closer, the black hole's gravity would begin to distort your view of the universe behind it through gravitational lensing. Stars and galaxies would appear to shift position and stretch into curved arcs. Light from objects directly behind the black hole would be bent around it, creating a phenomenon called an Einstein ring, a perfect circle of light surrounding what appears to be a dark sphere. This isn't just theory. In 2019, the Event Horizon Telescope collaboration captured the first actual image of a black hole's shadow against the glowing gas of the galaxy M87. That historic image confirmed what Einstein's equations predicted over a century ago. As you move closer, things get stranger. The black hole doesn't just bend light from behind it. It begins to show you the universe behind your head. The tremendous warping of space-time means you begin to see multiple images of the same stars, some in front of you and some apparently behind you, though you're looking forward the entire time. And the black hole itself? It wouldn't appear as a black disk as many imagine. Instead, you'd see a perfect sphere of darkness, what astronomers call the shadow, surrounded by a distorted view of the universe, like looking at reality through the most powerful fisheye lens imaginable. Now for the most fascinating part. What happens as you cross the event horizon? Here's where science may surprise you. If you were falling into a sufficiently large black hole, like a supermassive one, you wouldn't actually notice anything special at the exact moment you cross the event horizon. There's no physical barrier, no wall of fire, no dramatic change in what you see. In fact, according to general relativity, the laws of physics work normally in your local reference frame. The event horizon is only a special boundary from the perspective of distant observers. To them, watching from a safe distance, something very strange would happen as you approach the horizon. You would appear to move slower and slower. Your clock would tick more gradually, and any light coming from you would be increasingly red-shifted, stretched to longer wavelengths by the black hole's gravity. From the outside perspective, you would never quite reach the event horizon, appearing to freeze at its edge as your image grows dimmer and redder until it fades from view. This is the effect of gravitational time dilation taken to its extreme. But from your perspective, falling inward, time flows normally. You pass through the event horizon without any dramatic sensation and continue falling toward the center. The real trouble begins after you cross. Once past the event horizon, your fate is sealed. All possible paths in space-time lead to the center of the black hole, the singularity. It's like being in a river flowing toward a waterfall. Once you pass a certain point, no amount of swimming can prevent you from going over the edge. For a stellar mass black hole, the trip from event horizon to singularity might take less than a second. For a supermassive black hole, it could take hours or even days due to the much greater distance involved. During this final journey, you would experience tidal forces, the difference in gravitational pull between your head and feet. For small black holes, these forces would be lethal even before reaching the event horizon, stretching you vertically and compressing you horizontally in a process dramatically called spaghettification. But for supermassive black holes, where the gradient of gravity is less steep, you might survive crossing the event horizon with tidal forces being uncomfortable but not immediately fatal. As you continued falling, however, these forces would eventually become overwhelming. Here's where we enter one of the most profound puzzles in modern physics, the black hole information paradox, first identified by Stephen Hawking in the 1970s. According to quantum mechanics, information cannot be destroyed. The complete physical state of any object, the exact position and properties of all its particles, must be preserved even if transformed. But black holes seem to destroy information by reducing everything that falls into them to just three properties: mass, electric charge, and angular momentum. This apparent contradiction between quantum mechanics and general relativity remains an active area of research. Hawking proposed that black holes slowly evaporate through a quantum process, now called Hawking radiation, where particle-antiparticle pairs form near the event horizon. When one particle falls in and the other escapes, the black hole loses a tiny amount of energy over tremendously long timescales, far longer than the current age of the universe for large black holes. This process would cause the black hole to completely evaporate. But where does all the information that fell in go? Is it encoded somehow in the radiation? Is it lost forever? Or does it remain locked in some form we don't yet understand? In 2019, physicist Gerard 't Hooft and others proposed that information might be stored on the event horizon itself, like a hologram in what's called the holographic principle. This suggests that everything that falls into a black hole leaves an imprint on its boundary, a cosmic version of conservation of information. Our understanding of black holes continues to evolve with new observations and theoretical breakthroughs. In 2015, LIGO, Laser Interferometer Gravitational Wave Observatory, detected gravitational waves from two merging black holes, opening an entirely new way to study these objects. Since then, dozens of black hole mergers have been detected, giving us unprecedented insight into their properties and abundance. The 2019 image of the M87 black hole shadow by the Event Horizon Telescope was followed in 2022 by an image of Sagittarius A, the supermassive black hole at the center of our own galaxy. These direct observations have confirmed predictions from general relativity with remarkable precision. In 2020, Roger Penrose, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for their work on black holes. Penrose for proving that black holes are a robust prediction of general relativity, and Genzel and Ghez for providing evidence of the supermassive black hole at our galaxy's center. Perhaps most intriguingly, in recent years, theoretical physicists have proposed that the firewall paradox, a conflict between general relativity and quantum mechanics at the event horizon, might be resolved if the event horizon is actually a quantum mechanical object with properties we don't yet fully understand. There's something profoundly humbling about contemplating black holes. They represent the ultimate physical extreme in our universe, where our most successful theories of physics begin to fail and new ones must take their place. Standing at the event horizon forces us to confront the limits of our understanding. It reminds us that the universe contains environments so extreme that they defy our intuition and challenge our most advanced mathematics. Yet it's precisely at these boundaries, these horizons of knowledge, that the most exciting discoveries emerge. Black holes have pushed us to develop string theory, loop quantum gravity, and other attempts to reconcile quantum mechanics with general relativity in a theory of quantum gravity. The event horizon represents not just a physical boundary, but a philosophical one, the edge of the knowable universe. What lies beyond may remain forever inaccessible to direct observation, yet continues to drive our most profound scientific inquiries. The physics of black hole event horizons connects directly to our understanding of the early universe. The extreme densities and energies near a black hole singularity mirror the conditions of the Big Bang itself. Some theorists even propose that our universe might have formed from the other side of a black hole in another universe, or that black holes might give birth to new universes through a process called cosmological natural selection. This cosmic connection between the largest objects in today's universe and its birth billions of years ago reveals the beautiful unity of physics across time and space. The same fundamental laws that govern black hole event horizons also shaped the formation of the first particles after the Big Bang. If you found today's journey to the edge of a black hole fascinating, you'll want to explore these connections further. In our previous video, How Did the First Particles Form After the Big Bang?, we traveled back to the earliest moments of cosmic history to witness another extreme environment, the birth of matter itself from pure energy. The same quantum fluctuations that create particle-antiparticle pairs near black hole event horizons also gave rise to the first fundamental particles in the universe. The same interplay of gravity and quantum mechanics that puzzles us at black hole boundaries also shaped how matter emerged from the primordial fireball. If black holes fascinated you, you absolutely need to see our mind-blowing exploration of the Big Bang's first moments. Hit subscribe right now and watch How Did the First Particles Form After the Big Bang to complete this cosmic journey. The connection is incredible. The same quantum physics that creates Hawking radiation at event horizons also birthed the very first matter in existence. Don't miss this chance to understand how everything, including your own atoms, came from nothing. The video reveals secrets about particle formation that will completely transform how you see reality.